Hello, my name is Matthew Ding, and I'm a research assistant here at the Center for Theoretical Neuroscience at Columbia University. Today, I'm going to talk about the ways that network structure shapes dynamics in learning in recurrent neural network models, or RNNs. The particular connectivity statistics that we're considering in our work are firstly partial symmetry, which is equivalent to just saying the correlation between bidirectionally connected rate units. The second connectivity feature we examine is a self-coupling of the network. This can be interpreted as a way to quantify the clustering of neurons. If we use the RNN to model, say, an analogous spiking model or an actual neural network, then we can take a single rate unit as representing a bulk dynamic quantity of a subset of neurons in the actual network. Then the self-coupling term S represents the relative strength of connections within the neuron cluster compared to connections with outside members. Overall, these connectivity statistics seek to model the nature of connections within and between groups of neurons in neural circuits. Now, we are considering this RNN as a continuous time dynamical system, where the matrix J captures the connections between units, and the parameter G is a coefficient that determines the overall coupling strength, or variance of the elements of J. In these systems, we can define the attractor of the network. This is the set of points to which all initial network states converge towards over time. These RNN dynamical systems tend to be chaotic, which means that small perturbations grow exponentially in a seemingly unpredictable, yet deterministic way over time. And for this reason, the shape of the attractor is typically this convoluted fractal, and it's highly dependent on the particular realization of the network you're considering. One thing you could do is try to use chaos to your advantage and calculate averages over this entire attractor. In particular, we calculate the Lyapunov spectrum, which quantifies the exponential growth rate or decay rate of perturbations along each orthogonal direction in phase space, as indicated in this top panel here. And this gives the number of collective degrees of freedom of the network dynamics. We do this by counting the number of Lyapunov exponents that sums to 0. And the intuition behind this is that we are counting the number of dimensions for which the exponential growth rate of perturbations matches the exponential decay. When we relate partial symmetry and antisymmetry to the dimension of the attractor, we obtain two regimes in which partial symmetry and antisymmetry influences dimensionality. In the first, we consider the weakly chaotic regime, where the network still operates somewhat in a linear picture, since the distributions of unit activities are unimodal and narrow. Here, we can see that since partial symmetry increases the real parts of the network eigenvalues, it also has a similar effect on the eigenvalues of the Jacobian, which describes the growth of small network perturbations in tangent space over a short time interval. We increase the number of unstable directions that perturbations can grow in, and this leads to a greater number of positive Lyapunov exponents and a larger attractor dimension. The opposite relationship between symmetry and dimensionality occurs in the case where networks are strongly chaotic. This can be caused by a large value of G, as seen in the top panels, or by self-coupling, as seen in the bottom panels. It can also occur when the value of partial symmetry, or eta, is already very large, in this case, greater than about 0.5. In the strong chaotic regime, distributions of unit activities are either large variance, bimodal, or both. And this results in a large fraction of units for which the nonlinear transfer function tan h has a slope of almost 0. In this case, many entries of the Jacobian are almost 0 as well, and fewer directions have components of positive exponential growth of perturbations. In this regime, greater partial symmetry decreases dimensionality by further increasing the saturation of network units. Lastly, to study the effects of partial symmetry, antisymmetry, and self-coupling on input response and learning, we train RNNs to integrate a multidimensional input consisting of independently arriving Poisson pulses in 20 dimensions. The network is required to match the discrete value integral correctly at each time step with a linear readout. We use backpropagation through time with atoms to train the input, recurrent, and output weights, and we don't put any constraints on what gradient updates can occur. We find that networks across a variety of partial symmetry and self-coupling values can find diverse solutions to the task, although it seems that networks able to stay in the linear regime gain some performance benefits. We see this on a broader scale here, finding that antisymmetric networks tend to perform reliably better among all the parameters we tested. But we see that also a few quantities, namely the largest Lyapunov exponents and the spectral abscissa, or the largest real part of the eigenvalues indicated, for example, by the red arrows in the left plots, of the initial network before training, all account for much of the variation in training performance. This can be explained by the close relationship between Lyapunov exponents and the magnitudes of the gradients in backpropagation through time. Say if the Lyapunov exponents were too large, then gradients would explode. And this would generally be bad for learning, since large gradients means convergence on the actual minimum is unlikely. To recap our work, we model two major connectivity structures using RNNs, partial symmetry or antisymmetry, and self-coupling. These connectivity structures are observable and have possible functional significance in real neural circuits. We find two regimes in which partial symmetry and antisymmetry affect the chaotic dynamics in the attractor dimension of the network. And this depends on whether the network is in the weakly or strongly chaotic regime, which in turn depends on both the coupling strength and the strength of self-coupling in the network. Lastly, we find that training performance on high-dimensional integration tasks is aided by antisymmetry and hindered by self-coupling, which can be attributed to the value of the largest Lyapunov exponents. Whether this is a consequence of the relationship between Lyapunov exponents and gradient learning, or a consequence of the effects of antisymmetry or self-coupling on single unit properties such as variance or timescale is yet to be determined. Another possible future direction is to relate connectivity statistics to network's response to input in a more general sense than this integration task. And this can provide insight on how recurrent architectures in biological circuits process inputs and facilitate function and behavior. Lastly, I'd like to thank you all for listening to my flash talk. And I'd like to thank Laureline, Larry, and other awesome members of the Theory Center for helping to make my project possible. Thanks again for listening and take care.